So 165, so minus 165 is the phase point where we would have 15 degrees of phase margin. So I look for this point, minus 165. So it's at 0.112 rad per sec. I look at the magnitude graph, 0.112, and here the amplification is 29.4 decibel. I go back to the Simulink because I am lazy. I just copy the previous solution. Here I give a new name for the wire, so it was 15 degrees of phase margin wire. Here for the gain, then I will put the value what I read, 29.4. 29.4. So we have to pull this graph down, so there's a reason why it's 1 over. Okay. And similarly, we can do the last step. So the 19 degrees phase margin, we can use the calculator again. So it's 180 minus 90 is 90. So we have to look at the minus 90 degree. So here I look. Minus 90 is at 0.025. 0.025. 45.9 round. Okay, I go back. Here I change the gain. So 45.9 if I am not mistaken. Okay, excellent. And here I change the wire name to PM90. And I will use a new scope with 3 inputs to check what happens. What are the differences between phase margins? Like this. And here you can see view legend. And as you can see, if you have little phase margin, then it oscillates more and more. Then we have medium and maximum phase margin. The maximum phase margin is very stable. We don't oscillate so much. But indeed we see that the error is larger. Sometimes you can have system where you cannot allow stability issues, you cannot allow oscillations, then you have to stick with higher phase margin. Okay. And the next is to do an integrator and a differentiator. So a PID controller. I am going to show now only the PI controller, and based on this you will be able to do the PID controller. So I start with this structure. Now I remove the rest, I don't need. Okay, and what we will add here is this term. This we have already. This is a simple wire plus the integrator. So I move these blocks just to make a little bit more space like this. Here I will need an additional add block or sum as you prefer. Plus. Connect back. We have this branch, so it's like this. And we need the integrator. And the integration time, usually you can choose the largest time constant as an integration time. So this is a transfer function. Ideal integrator is 1 over integration times s. So here I put 0. this, and they connect back. And how to read the time constant? For this, we will use the pause 0 plot here and show the results. So we can see that here we have, and here we have also, and pole, and the dominant one is the highest value. It's this. I zoom in, and I see that it's minus 10 times 10 to the power minus 3. So this is 0.01 minus. And the time from this is 1 over the pole value in minus. So reciprocal of this is minus 100 times minus is 100. So the integration time is then 100 here. Oops, sorry. No, the problem that we introduced a new element, and you can see that things have changed. Because we have a new element, we changed also inherently the phase margin. And for this, we can double check if the phase margin is still good. So I will use this setup. I will assign here a new port, linear analysis port, open loop input. Here I will assign a new output. So linear analysis port, open loop output, like this. And I add a new Bode diagram. And let's say we can start from 0, and I will reset this value. So I put here 1, and I check what would be the ideal gain. So I remove. What you can see here is that we have these blocks, and you have to identify what is what. Here I put the input at step here after the add block, so we will need the add block. I remove this, and transport delay and transport delay 1, so I need these two items. And again, in algorithm options, you use exact delay. Show the Bode plot. You can see that the change of the Bode plot changed because of the integrator. And I look for the 45-degree phase margin, where it would be. It would be at minus 135 degrees. Here, the crossover frequency for this should be 0.0558. So I look at that. I look for the closest one. And what I see here is 38 decibel. I go back here. I change the gain. So I use the formula to convert to real numbers. So then we had here 38 over 20. 38. If I do this, then I push the Bode diagram up, but we have to push the Bode diagram, the magnitude graph down. So I use the reciprocal. And voila, what we see that now the settling time went from the P case was something like 250 seconds. It went around to 120 seconds, and we have less oscillation and exactly zero finite error. Okay, the rest I hope you can do yourself. Thank you for your attention.